All right, welcome back. In this video, we're going to continue our discussion of the continuous distributions. And we're going to focus today on the gamma distribution, which is kind of a family of distributions. And there are a lot of different distributions within this grouping or classification. So we'll spend a little bit of time just kind of explaining to you what the gamma is, how you identify it, and then we're going to jump straight into some of the more specialized cases that actually have applications to engineering. All right, so as we said, the gamma distribution is basically a family of distributions in which there's a skew associated with, and what they do is they will parameterize part of the function in order to move the skew around. Now, like I say, we're not going to worry too much about the mathematics behind it or the semantics of how it works, but I just kind of want to give you kind of a basis of it. So, here we have a basic skewed function, okay, and typically you'll know whether a function is skewed or not. In fact, you can use if you plot the data of of a survey or a test result or something, you can generally get a sense of, is it positive skewed or negative skewed or something like that. In fact, some of the more important skewed distributions that you'll encounter in engineering are the exponential and the log normal. Will be two of the bigger ones, exponential especially. Okay, so the gamma distribution, though, is defined based off of this gamma function. Okay, and again, we have a parameter that goes into this that's going to be called as alpha. Okay, and so the basic form of this is the integral from infinity to 0. Now notice it doesn't go negative, it's from 0 and up. So these are really good for like time-based distributions in which you can't have a negative time. Okay, and then it's x to the alpha minus 1 multiplied by e to the minus x dx. All right, and so a couple of basic properties that are defined. Again, I'll just kind of list these here. We don't use these a lot, but just so that you can say that you've seen them, is that the gamma function evaluated at some alpha is equal to alpha minus 1 multiplied by a gamma as a function of alpha minus 1. It's a little bit unusual in that regard. And that the gamma of an n is equal to n minus 1 factorial. If you look at these pieces and you keep kicking it down, you can see that we're basically building the factorial representation. And then that the gamma of 1 over 2 is actually the square root of pi. Okay, and again, we did have some restrictions that alpha has to be greater than 1, and n has to be greater than 0 in all of these. Okay, and so the distribution itself then, if you turn this, start playing with the random variables and actually execute this function for different values of x on here, you can see that the probability distribution is basically defined based off of two parameters. Okay, we're going to call one is alpha and one is beta. Okay, I think it's actually a different alpha than what's up here, but the basic form looks something kind of like this. Okay, and so we get the distribution of x with the two parameters alpha and beta. It's going to be 1 over beta raised to the alpha power times gamma of alpha, where the gamma function was defined earlier. And then it's x to the alpha minus 1, and then it's e to the minus x over beta. Okay, where x has to be greater than or equal to 0, and alpha and beta are both greater than 0. Okay, and then finally, for a gamma distribution, we know that the expected value of x then, or the population mean, is going to be alpha times beta. So this is how you can start to get those the parameters on this. And then our variation of x is going to be sigma squared, which is alpha times beta squared. So you can see that if you plot a bunch of data points and you actually tally up the expected value of x and the variance of x, you can quickly recover alpha and beta by solving these two equations simultaneously. And then once I have these alphas and betas, then I can go in and I can actually define the actual probability distribution of this thing. Okay, that's some form that looks something kind of like that. All right. So now, like what we did with the normal distribution, there is a standard gamma function on this, okay, and for the standard gamma distribution, you're going to set beta equal to 1, and so then the CDF we can show as being this formulation. Again, we don't use this a lot, but again, just so the notes are complete, that's why we're going over it, is that we have the CDF is based on a parameter x and a parameter a, or alpha, okay, and so it's 1 over gamma of alpha, and then integral from x to 0, of y to the alpha minus 1 e to the minus y dy. And again, we're worried about x's being positive. And so then, just like before, the probability of a random variable x being less than some value is basically the CDF function that we just defined for that value given alpha and beta. Okay, and since beta is 1, this becomes the function of x divided by beta, okay, and then alpha, and I can solve this thing as a standard gamma type function. And again, we don't do a lot with it, but just so that we have it. Okay, now within this family, for specific values of alphas and betas on here, okay, we have a whole slew of different distributions that have have their merits and have their uses. Okay, the first one we'll talk about is the exponential distribution, and this one is widely used in engineering and science. Okay, it's based off of a parameter that they're going to call as lambda. Okay, and lambda is always positive, so you can kind of think of this as being like that alpha function on here. on here, and so our probability distribution of x and lambda is 0 for anything when x is less than 0. Again, it has to be positive. And then it's lambda times e to the minus lambda x anytime the x is greater than or equal to 0. Okay, now this formulation comes out of what we showed with the general gamma. When alpha is 1 and beta is 1 over lambda, you will get this formulation and this CDF back for doing it. So it's a specific subset of the gamma distribution or the gamma family. Okay, and then the CDF then is x and lambda, and then it's 0 when x is less than 0, and of course then it's 1 minus e to the minus lambda x whenever x is greater than 0. And again, this is how you figure out the CDF for a particular value of x. So they've done the summations and they've done the integration when they build this. So that's a very, very popular one that will work. Okay, another one that shows up in statistics quite a bit, especially when we start talking about distribution of the mean or distribution of the variance, is the chi-squared distribution. Okay, and so this is used in statistical modeling or for inferring outcomes based off of sample data. If I can identify that it's a chi-squared distribution, then I can jump straight to this and we can actually start finding probabilities and use that to solve problems or answer questions that we may have. So the distribution for this guy is going to be x and some parameter. They usually use it as this kind of scripted v thing. It's a new in u character. Okay, and so it's 0 when x is less than 0, and then it's 1 over 2 to the new divided by 2 power, and then it's gamma of nu divided by 2 for this one. All right, and that will give you a chi-squared distribution, and that's a particular distribution or form of the general gamma when alpha is nu over 2 and beta is 2. Okay, so again, you just kind of play with the alphas and the beta parameters on this, and you can start to fit these curves into families and start to identify certain sets the way that they're set. Now, this nu is basically it's a positive integer, and it represents the degrees of freedom of the random variable. Now, again, we're not going to worry about that a whole lot in the mathematical terms of what that means, but just so that you can say that you've seen these. Okay. Other distributions that show up, you'll see something called the Weeble distribution. Okay, and so that's used in engineering testing. And so just kind of more of the same, that based off of a parameter of alpha and beta, it has a distribution of again 0 when x is less than 0, and then alpha over beta to the alpha multiplied by x to the alpha minus 1 multiplied by e to the minus x over beta, okay, all raised to the alpha power. Okay, and so if you notice, everything has an x to some alpha power and an e in it. Okay, and so that's the kind of a general indicator of the form that you're starting to kind of see. Okay, CDF, again, it's kind of looks very similar to the exponential, 1 minus e to the minus x over beta raised to the alpha power. Okay, and then the expected value of the Weeble, then the population mean is going to be beta times gamma of 1 plus 1 over alpha, and the variance or sigma squared will be beta squared. Okay, and then that gets multiplied by the sum of these two quantities, 1 plus 2 over alpha minus gamma squared of 1 plus 1 over alpha. So it's a little bit of a different animal. Again, you'll see this from time to time, but we're not going to do much with it in this series. Okay, another one that shows up from time to time is the log normal. And so basically what they do is they say that if you have a random variable x, okay, if y is equal to the natural log of this guy, and it is also normally distributed with a mean and a standard deviation, okay, then x is said to be log normal. Okay, and if that's the case, then the distribution looks something like we would expect: 0 when x is less than 0, and then it's 1 over 2 pi, and then times sigma, okay, there's sigma x times e to the minus natural log of x minus mu quantity squared over 2 sigma squared. If you look at this, this looks like that Gaussian. The only difference is right here, okay, that natural log that shows up on the x term. Okay, and then the CDF, which will be x and then alpha and beta, is 0, and then you can kind of do what we did with the standard normal, except now, again, instead of plugging x in, you're plugging in log of x and finding the probabilities based off of that. So that's exactly what we did with the normal distribution in the last video. So if you don't remember that, take a look back at that video, and it'll explain this whole standard normal technique and for calculating the cumulative a whole lot better. So I'll refer you back to that one for now. Okay, all right, so let's give one a try and just kind of see what you can kind of do with this. Okay, so suppose that we're looking at successive arrivals at a drive-up window. You know, maybe they're at a restaurant or a McDonald's or something. Okay, and we're going to say that we're given that it's an exponential distribution. Now, without this given statement, this looks like a Poisson problem, okay? But what we're also doing is, we're recognizing that when we had the Poisson distribution, we were counting the number of pulses, the number of arrivals or the number of departures. What we can do with an exponential distribution is I can start calculating times between arrivals. Okay, so it's not so much the number of arrivals, but rather how long exists between them. Okay, so for this experiment, we're going to say that x is exponential based off of a parameter x and a lambda that is being given as 1.0. Okay, so this is part of the given. Okay, so our random variable x is going to represent the time between two successive arrivals. Okay, measured in minutes. Okay, so the first question asks us, well, what's the expected value of this? Well, the expected value of this scenario then is going to be 1 over lambda, which is basically 1 minute. So that's the expected time between two successive arrivals. Okay, we can calculate the variance as 1 over lambda squared, and that's equal to 1. Okay, so then I can come in and I can play the probability games that we've played in previous videos, where I'm taking the probability that x is less than or equal to 4 minutes as being then a cumulative of 4 with a lambda parameter of 1. And so then 1 minus e to the minus 4 power is that equation. And so we find out that the probability of it being less than 4 minutes between arrivals is 0.982. It's 98%. Okay, so you're almost up to guaranteed, but not quite there, but pretty likely, if you will. Okay, then we can go in and we can play the game of the probability falling between a range. So now I took 2 minutes less than x less than 5. Okay, and so as you would expect, this is the CDF for 5 minus the CDF for 2. Again, we're not worried about the equal signs on this. Notice this one didn't have it, but this one did. And again, it doesn't matter, okay, because the singular values in continuous distributions are 0. Okay, and so then if I plug in my equations, 1 minus e to the minus 5 minus 1 minus e to the minus 2, I get the equation e to the minus 2 minus e to the minus 5. And so that becomes then a probability of 0.129. being the probability of it falling in that range as well. Okay, so you can see a lot of the probability falls up in that first quadrant. For x less than 1, you'll get a lot of your probability will fall into that. So all right, okay, let's try another one. Okay, so we've got another exponential. Okay, I've got an electronic system of 5 pieces in series. One piece fails, the whole system fails. All right, so it's a serial connection. So here's piece 1, 2, 3, 4, and 5. Here's my in, here's my out. Okay, and what we want to know is we're to define an event A sub I being the scenario where the ith component lasts at least t hours. Okay, that is kind of an expected life kind of problem. Okay, and we're going to assume that all of our AIs are independent, meaning that if this guy falls, it doesn't automatically blow out all the others. So we have no chain reactions. Now, in a physical setting or a physical type of problem, generally we can't necessarily make this assumption, but just for the sake of the math and showing kind of some of the properties of this distribution, I wanted to kind of eliminate it as a possibility. All right, so what we're going to do is we're going to define a random variable x as the time t when the system fails. So if we start measuring time now at time equals 0, then time t is the time when the system will fail. Okay, and so we're going to say then, in this case, that the component, the random variable x, is exponential on x, and it has a lambda of 0.01. So it's basically a 1% kind of arrangement on this thing. Okay, so if we can define the lambda, then we should be all right. Okay, so what we want to do is we want to write the event for when x is greater than t, when my time is greater than this expected t value that we have. Okay, and so for x to be greater than t, okay, for the system to fail, then any one of the 5 have to fail. So in order for the whole system to work, all 5 have to be functional. So the event for x lasting longer than any one of the components, it's going to be A1 intersect A2 intersect A3 intersect A4 intersect A5, which is what we see right here. Okay, sorry, here. Okay, you notice then that I drop down and say, what's the probability of this event? Okay, and so now we're just doing the probability of all of that, and you'll notice that I've written this in a shorthand notation, and you may or may not have seen this. This is called the product operator. Okay, so we had the summation operator, which was this, in which I did, x1 plus x2 plus so forth. This is now, the product operator is now, I would be doing x1 times x2 times x3, so forth and so on. So this is a multiple. So if we say that they're all independent events, then we know that the intersection of all 5 of these is basically the probability of each individual one multiplied by all the ones in the sequence. So that's why we can do a product operator on here. Okay, so what happens is we know that for one event, for one component, that it has a form, the probability of that element lasting is e to the minus 0.1x. Okay, so again, that's my lambda, it's minus lambda and x. On that, okay, is the probability of basically of one piece failing before time t. Okay, now if we go in and we apply our product rule, then the probability of the whole thing of x being greater than that time t, it's going to be item 1 probability multiplied by item 2 multiplied by 3 by 4 and by 5, and I can do the math and do some algebra and combine all these, and I get that the probability of x greater than or equal to t is then e to the minus 0.05x. Okay, so it's kind of an interesting little observation if you notice it, right? If we look at this, we had an individual component here, okay, that was exponentially distributed and had its own lambda value, if you want to call that as lambda 1, lambda 2, lambda 3, or whatever. But at the end, when I chained all those things together in the series, the entire system takes on the exact same form. Okay, it's still exponential, but what changes is now this guy, 0.05. And where did that 0.05 come from? What was the sum of all those 0.01s in these? And those were the lambda values. So what happens is that the system becomes exponential, okay, but it has a new lambda value for the system level, which is the summation of I equals 1 to 5 of all of my lambda I values. So basically this becomes, lambda 1 plus lambda 2 plus all the way out to lambda 5. Okay, and so that's kind of cool. So even though in our problem we said they were all the same, now they don't have to be. I mean, this guy could be different than this one, is different than the next one. Okay, and so we're in good shape for being able to kind of simplify this. Okay, so then with this being the probability of x lasting longer than t, the time probability of it failing before t then would be a CDF, which is what we see here. And that's the probability of x less than or equal to t. So it would be 1 minus this guy. And so we can say that the probability of it failing is 1 minus e to the minus 0.05 t power. Okay, would be a way of being able to write this CDF for the survival time of an electronic system. So it's kind of cool, some of the properties that start to kind of show up on this. Okay, all right, the last one then is kind of rehashing, well, what happens if instead of 5 components, we had n number of components having an exponential lifetime with parameter lambda on there? Well, in that case, this cumulative becomes 1 minus e, and instead of being the sum of lambda I, it now becomes n times lambda, assuming that they all have the same lambda. It's still that summation symbol that we saw. This is still at play, but now I can quickly, for 100 or 1,000 components all having the same lifetime or lambda parameter on these, and looking for a variable t, this was the equation that we had. So now we can say that x is exponential with lambda equal to n times lambda 1. Okay, and again, that assumes that they're all the same, and then you're off to the races. You can chain as many of these things together as you want. And so that's one of the nice things about the exponential distribution is I can merge and explode and subtract and combine lots of different components very, very easily and very, very quickly, and the math doesn't get any harder than the base system that we were working with. So anyway, that gives us a little bit of a taste of some of the gamma family functions. Okay, like I say, we don't do a whole lot with the gamma function itself, but understanding how to do the exponential and how to do some of the others, can be useful, especially the exponential, and that's why I thought I wanted to kind of touch base on this. So we'll stop there for now. We'll continue our discussion into continuous probabilities in the upcoming videos. So as always, if you found it useful, toss us a like down below, and then please be sure to subscribe to the channel, and we will see you next time. So anyway, have a great evening. Talk to you later. Bye.